Hi, my name is Janavi Babalori.
My name is David Lin.
My name is Antonio Boucher.
And I'm Sarah Stranger, and this is Automated Sensor Technology for the operation of smart homes.
The purpose of our project was to eliminate any wasted energy and lower potential household costs through implementing smart home technology. Our sensor system has a few main sensors. We have a temperature and humidity sensor, a door sensor, a light sensor, and a color sensor. All of these sensors work together to optimize energy usage in the home. We also have a smaller purpose to create an Internet of Things, so all of these sensors can communicate their data to a central computer, which can then output decisions.
So to provide some background for our project, when we discuss the Internet of Things, we're specifically discussing our implementation where we have an array of sensors, simple sensors that all collect data from the environment, and then they all send their data to one central or one master computer, however you want to describe it. This master computer takes the multiple input streams of data and makes conclusions based on all of the information that it couldn't otherwise. We created our sensors out of basic electronic components. Most important to our component was the resistor, which is a simple electronic circuit component that reduces the electrical energy in a circuit by converting some of it to heat. There are many different types of resistors like thermistors and photoresistors, which change their resistance based on outside values like temperature and light, respectively. We also use reed switches, which are switches that only allow electrical current in presence of a magnetic field due to the small metal flaps that are pulled together by the presence of a magnetic field. We also use a humidity sensor, which determine the amount of water in the air based on the changes in the electric conductivity of ion salts. We connected our electronic circuits to Arduino Uno boards, which are small programmable microcomputers. We programmed these with the Arduino software, which allowed us to set instructions for looking at inputs on analyzing inputs and then sending outputs based on that data and computations and other information of our choice. In order to create a more pleasing graphical user interface, we used the Java coding platform for its high fidelity with images. And we obtained the Arduino data in Java using the JSerial.com library, which added functionality for Java to look at the COM port, which is how Arduino communicates with the computer.
In designing the door monitoring system, the first step was actually wiring the reed switch. And after we were able to wire the reed switch, we tested it with an LED. So when a magnetic field was brought close to the reed switch, the circuit was closed and the LED was able to light up. And when the magnet was taken away, the circuit was open and the LED did not light up. Through step 3, we integrated a buzzer into the circuit so that when the door was closed and the magnet was close to the reed switch, the buzzer would not buzz. And when the door was open, the buzzer would buzz, alerting the user to close the door. Through step 4, we coded for a 10-second delay so that the buzzer would start to buzz 10 seconds after it was open, as not to irritate the user. And lastly, we set up the sensor in a box, as shown in the diagram below, to replicate the surroundings that it would be placed in an actual house.
The next sensor that we built was a temperature sensor. And for the temperature sensor, we placed a 10,000 ohm thermistor, which means that its resistance at 25 degrees Celsius is 10,000 ohms, in series with a 10,000 ohm resistor. The equation above illustrates how we determine the temperature in Celsius of the thermistor, where RT is resistance of the thermistor and A, B, and C are unitless constants. In addition, the graph to the right illustrates the relationship between resistance and temperature, which we determined from our trials. The next sensor that we built was a humidity sensor, which consisted of a DHT11 humidity sensor. The DHT11 measures the relative humidity, which is a percentage, in the air using the above equation. RH equals rho W over rho S times 100%, where rho W is the density of water vapor and rho S is the density of saturated water vapor. In addition, the circuit diagram to the right illustrates the complete temperature and humidity sensor. Finally, we tested these sensors by comparing the outside temperatures and humidities returned by these sensors to real-time data provided by weather stations in Piscataway, and from our comparisons, we determined the percent error to be about 2.6%, which is relatively low and demonstrates that our sensors are relatively accurate. The next sensor we built was a light sensor. And for the light sensor, the brightnesses of the LEDs are adjusted based on whether the ambient light levels in the room are greater than or less than what the user requests. The light sensor circuit consists of a 10,000 ohm resistor, followed by a 10,000 ohm photoresistor, and then 6 blue LEDs in parallel, as shown in the circuit diagram below. The Arduino reads voltage changes across the photoresistor and then converts these voltages to photoresistor readings with arbitrary units of brightness, ranging from 700, which is extremely bright, to 1018, which is extremely dim. Next, the Arduino continually adjusts the brightnesses of the LEDs until the photoresistor reading falls within 5 of a target value. The user input is used to determine this target value, which is one of 10 interval light values between 700 and 1018. When the photoresistor reading is greater than the target value, the brightness of the LED is increased by increments of 2 until the maximum LED value of 160 is reached. Likewise, when the photoresistor reading is less than the target value, the brightness of the LED is decreased by increments of 2 until the minimum value of 0 is reached.
Next, we made a color sensor, which is made up of 4 voltage dividers and an LED. Voltage dividers are made up of a photoresistor and a resistor in series. And because a photoresistor changes its resistance based on how much light hits it, you can measure the voltage drop to see a color when you combine it with a color filter. And what a color filter does is it filters out all wavelengths of light other than your desired wavelength. So, for example, red, if we put red on, it would only see the red light. So to convert values that we see around us to color, we used RGB alpha values, which is red, green, blue, and alpha, which is brightness. And to, for example, measure red, we would put a red color filter over a photoresistor, and to scan pure red is the maximum of this, which would be 255, because it ranges from 0 to 255. And when you measure pure red, you'll get your maximum, and when you measure black or pure blue, where you'd have the absence of red, you get your minimum. So when you make a photoresistor for each individual color, as seen here, you can take these values and coordinate the values that you read from the voltage divider, which could be any number from like 1,000 to 700, and you find what the max is and what the min is, and you convert that value to a value from 0 to 255 accordingly. And that's read through these pins. And using that, you can import it to Java, which is what we did, and display that color on screen using these values.
Bluetooth is an essential enabler of our Internet of Things smart house because Bluetooth relays data directly from an Arduino board to a central computer. Bluetooth is radio wave technology that permits wireless short-distance communication. Not only do Bluetooth modules use relatively little power, which is a great plus for our project, Bluetooth devices automatically detect one another, and up to 8 Bluetooth devices can communicate with each other at once. For this project, the module that we used was the DSD Tech HC05 Bluetooth module, which consists of a button, an LED, an antenna, and 6 pins. The module acts as a virtual COM port, which is a serial port that transmits data 1 bit at a time. Finally, on the Bluetooth module, the TX pin transmits serial data to other Bluetooth devices, while the RX pin takes in serial data from other devices.
Our electronic setup consisted of 3 boards, the first of which transmitted data through Bluetooth from an outside board, which is intended to measure outside temperature, humidity, and an outdoor door sensor. Our second board right here measures temperature and humidity indoors and also contains the light sensor. The third board right there is home to the color sensor and also the indoor reed switch or door sensor. So the data from all of these doors and all of these boards comes together in the graphical user interface in which the user is able to customize their system and view the data collected. So first, the user can set a temperature and humidity if they'd like, and the program will then make decisions based on this and the temperature surrounding the house. So For the decision-making, our system takes into account outdoor temperature to make the home as energy efficient as possible. So if the outdoor temperature is above the desired, we'll turn on the air and then send the user an alert to close their windows in order to keep the air in and conserve energy. If the outside temperature is at or below their set temperature, the air will turn off, and then the user will be alerted to open their windows and allow natural air to flow through the house and cool it naturally, eliminating that extra energy usage. The user can also specify a humidity, and the same idea goes for above and below. However, they don't need to if they don't want to. Next, on the graphical user interface, we have the light data, which allows the user to set their brightness from 1 to 10, and it also displays how much power is being used. So out of the total power that can be used, it would be like 50% or 100%. And this is sent to the Arduino once they put it in. It also has the door statuses, whether they're open or closed, and if the door happens to be open, it will provide the user right below the closed or the open with a timestamp. So these are really intended to be on like a front door or a refrigerator, so if it's left open for some reason, the user can know how long and like gauge what might have happened because of that. Lastly, on our GUI, we have a color sensor, which allows the user to, when they press start, it will display in real time the color being sensed, and it will give the user RGB alpha values in case they want to recreate that color, and this can be used for color matching within the home. So our graphical user interface was really designed to be as user-friendly as possible and to be something that highlights the most important aspects of the home. So whether things are on or off, what's open and closed, and not to really throw anything too extra in it, to keep it first aesthetically pleasing, user-friendly, and to make people want to use it and make their homes more energy efficient, because it's nice that it saves energy, but people also like cool stuff. So, yeah.
At the conclusion of our experiment, we were able to successfully operate all of our sensors, and we found that the temperature and humidity sensors specifically were quite accurate. We were able to utilize equations, the ones you saw before, were from the manufacturers, which meant that they were built very specifically for the sensors and ergo were quite accurate. Our color sensor, we were able, through a large amount of calibration, to get it to a very, very specific setting, and we were happy that we were able to reach that point. On the other hand, our light sensor, while it operated well, LEDs aren't very effective at showing different brightnesses, and therefore the system where the LEDs would brighten or decrease power depending on the current light level wasn't as specific as we could have it, because there were only like no more than 10 possible brightnesses for the LED. Incandescent bulbs are more effective at having ranges of light. And overall, we didn't have very high quality components, so of course at a certain point we reached a point where we couldn't make our systems any more accurate due to the inherent variation of the sensors. We took trial data for both of our color sensor and our temperature sensor, comparing actual values to values returned by the sensor, and through our average differences in values we came up with an error of actually about 3%, which we were very happy with, though we didn't have too large of a data segment, so this number's probably varied a bit, but we were very, very pleased with how far we could get our calibration to reach.
In addition to our project results, we also want to touch on future applications and improvements. So firstly, we like to cover up the sensors, especially the outdoor temperature and humidity sensors. We want to make sure that they're protected from any harmful weather conditions. Secondly, we also want larger scale applications. So as we mentioned, we have a light sensor, but the sensor can only change the brightness of LEDs. In the future, we want the brightness of actual light bulbs to change so that users can implement this in an actual household. Next, we also want to reduce user interaction. So as we already said, the GUI emits an image as soon as the air conditioning turns on for the windows to close and vice versa. In the future, we want this to be automatic. So as soon as air conditioning turns off, we'd want the windows to open and allow for cool air circulation. Next, we also want to include more sensors. So in addition to the main sensors that we touched on before, we want to include touch and noise sensors to increase accessibility and energy efficiency. And lastly, we also want better wireless connection to have a faster relay of data across larger distances. For acknowledgements, we'd like to thank our project mentor, Einar Magnuson, for guiding us through the project and through any challenges. Also, we'd like to thank our research coordinator, Brian Lai, and our residential teaching assistant, Nicholas Ferrero, for assisting us with the paper and presentation aspects of our project. We also want to thank the directors of the program, Dean Rosen and Dean Antoine, for giving us this great opportunity to conduct research over the summer.
We would also like to thank Rutgers University, the Rutgers School of Engineering, the State of New Jersey, Lockheed Martin, Silverline Windows, Rubix, other corporate sponsors, as well as NJ GSET alumni for adding to this amazing experience and providing us with funding throughout GSET.
We really appreciate you listening to our presentation, and we really hope you enjoyed it a lot.
Questions?
Yes.
What's the color sense? Like, what exactly are the benefits of the color sensor?
So it can be used for like color matching around the house if you need to like match paint or match like interior decoration. And
Since it was more of a prototype, our application hasn't been specified to the degree for the other sensors.
Well, I would just like to be notified by Bluetooth when my refrigerator's open, so whenever you have that ready.
Second that, first one.
Okay.
Thank you, it's an amazing presentation.
Thank you.
I noticed that you mentioned about color sensors, right? Color sensors are usually very, they're a function of ambient light, right? So you go here, red would be like, burgundy. How did you manage those aspects of ambient light to make sure that you're...
so our color sensor, so the circuit board for it, first of all, is covered in black electrical tape to prevent, to absorb any light, and it also has like a rim around it to block out any other ambient light, and the LED is just inside so it can sense that color and this white light. So when you use it, you ideally hold it like if I was to sense my arm, I'd hold it right up to my arm, trying to seal out any ambient light from getting in, which prevents any interference. Anybody else?